So when we're talking about IMFs, the big thing to keep in mind when dealing with IMFs is the difference in polarity. So when we talk about intermolecular forces, remember inter meaning between the molecules here. So it's not actually inside the molecule, that'd be intramolecular. So we're focusing on in between the molecules. So it kind of gave you a diagram here to show you the breakdown of intermolecular forces between polar and nonpolar molecules. So when you have polar, you're going to have a permanent dipole. The big thing that we're going to focus on here is a dipole-dipole interaction here, where we have polar molecules. When we have a polar molecule, we know that there is a difference in electronegativity, and then based off from that difference in electronegativity, we're going to have some type of attraction. So we know polar molecules, there's a dipole attraction to the other dipole. The molecules have a difference in electronegativity value, thus causing that interaction between those. Okay, again, this is an electrostatic attraction between the molecules, just like that is present inside of ionic compounds. The other form that we have is the strongest form, which is hydrogen bonding. Remember, hydrogen bonding is like a dipole-dipole interaction, but it's much, much stronger, so much that it's almost similar to the strength of a bond. When we have hydrogen atom, it is going to be either bonded to nitrogen, oxygen, or fluorine, and that difference, the largest difference obtainable possible in a covalent bond, is then creates that large attraction between the other molecules. So when we have that partial H attracted to one of the lone ends, O's or F's, you get that very large electrostatic attraction between the molecules, causing them to be joined together very closely. The last form that we talk about is van der Waals forces of attraction. Remember, this is where you have a temporary dipole. Okay, it can be induced based off from a polar molecule, or it can be induced by nonpolar molecules being very close together. When you have nonpolar molecules very close together, based on the size of their electron cloud, you can see there's a pushing of the electrons. Okay, so nonpolar molecules go into what's called an induced dipole attraction. They have random movement or dispersion of electrons, thus there's an instantaneous negative charge on an atom and a temporary dipole. So based off from that dipole, now there is an attraction. Okay, again, the result is a very, very, very weak electrostatic force of attraction between the molecules. So when we look at this, the big portion of this and why we talk about intermolecular forces is the idea of phase change. So I don't want you to really look at the delta H, which is a change in heat, but I want you to look at the orientation or the proximity of particles as they go from a solid to a liquid to a gas. If you have a very strong force of attraction or intermolecular forces within, you're going to be typically in this solid phase, or maybe a liquid or a gas, but you have to put in much more energy to cause those particles to spread out from one another, meaning that you have a strong intermolecular force. So to summarize that, your phase is directly related to the strength of your intermolecular forces. The stronger your intermolecular forces, the higher your melting point, the higher your boiling point, because you have to put in more energy to separate these particles, to change them from a solid to a liquid to a gas. So the reasoning behind intermolecular forces, again, is it affects the phase change of a substance. The stronger your intermolecular forces, the harder it is to change from a solid to a liquid to a gas. And that is the intermolecular forces information that you need to make sure you're comfortable with for your exam.